Welcome to the Distributed Cloud Computing video lecture series. And in this video lecture, we are going to see the topic relation of distributed systems to parallel multiprocessor or multi-computer system. So today we will explore the relationship between distributed systems and parallel systems, particularly focusing on multiprocessor and multi-computer systems. While these systems might seem similar, they have distinct characteristics and applications. We will go through each system, how each system operates, compare their features, and highlight their real-world uses. Characteristics of parallel systems. Parallel systems involves the simultaneous execution of tasks using multiprocessors. The key here is that tasks are divided among processors and executed in parallel, leading to faster completion. Parallel systems can be categorized into three main types: multiprocessor systems. Multiple processors share a common memory. 2. Multi-computer systems. Multiple computers are linked by a network, each with its own memory. Number 3. Array processors. These are specialized processors that work synchronously on large sets of data. A real-world example of multiprocessor systems would be the supercomputers used in weather prediction models. Multi-computer systems, on the other hand, power cloud-based applications like Google Search, where data is processed across many servers. Multiprocessor systems. In multiprocessor systems, multiple processors work together to process information faster by sharing a single memory space. This is known as shared memory architecture. Think of it like a group of people working on the same project using a shared whiteboard. Everyone can see and update the information in real time. The key features includes uniform memory access. Every processor accesses memory at the same speed. Shared operating system. All processors run under the same operating system. Homogeneous processors. All processors are identical. An example of this is IBM's Blue Gene, a supercomputer that uses multiprocessor architecture to handle complex simulations like protein folding. Multi-computer systems. On the other hand, multi-computer systems consist of several independent computers that do not share memory. Communication between these computers is done through message passing over a network, much like how different offices might communicate using email or chat. Key features of multi-computers include non-uniform memory access. Memory access speeds can vary depending on the processor's proximity to the memory. 2. Message passing communication. Instead of shared memory, nodes pass message to exchange data. A perfect example here would be a Google Cloud infrastructure, where individual computers or servers work together in a coordinated fashion, but each has its own memory. These systems are great for large-scale web applications and services. Array processors. Array processors are highly specialized type of parallel systems. These processors work in sync using a common clock to process data in parallel. Imagine working together in a relay race with everyone passing the baton in perfect coordination. Array processors are ideal for tasks that involve large amount of data and repetitive operations such as digital signal processing, so which uses in audio or video processing and telecommunications. Image processing. So here large images are divided into blocks and each processor works on a part of the image. A real-world example would be video encoding, in which array processors handle multiple pixels at once, processing each frame simultaneously for faster video compression. Key difference between parallel and distributed systems. Now let us look at the key difference between parallel and distributed systems. While both systems use multiple processors or computers, they have fundamental distinctions in architecture and operation. Number 1. Communication. Parallel systems may use shared memory or message passing, while distributed systems rely almost exclusively on message passing. Number 2. Coupling. Parallel systems tend to be tightly coupled, meaning the processors or computers are closely connected, whereas distributed systems are loosely coupled with nodes spread across different locations. Number 3. Memory access. Parallel systems use shared or non-shared memory, but each node in a distributed system has its own memory. Number 4. Scalability. Distributed systems are highly scalable since they are designed to expand across geographically diverse locations. For instance, high-performance computing clusters like NVIDIA GPUs in AI research work in parallel to process large datasets, while servers like Netflix operate over distributed systems to manage content delivery to millions of users. Advanced architectures for multiprocessor systems. Advanced architecture enhance the efficiency of multiprocessor systems. Two popular types are: number 1, multi-stage interconnection networks. Examples include Omega networks and the Butterfly networks. These networks efficiently route data between processors, minimizing delays and avoiding bottlenecks. Number 2, hypercubes, a multi-dimensional architecture where each processor is connected to multiple others, providing efficient communication and fault tolerance. These architectures are often used in scientific computing and simulations, such as modeling the behavior of molecules in chemistry or physics. Applications of parallel systems. Parallel systems have a wide range of applications. Here are some examples. Scientific computing, large-scale computations like simulating climate change or analyzing DNA sequence. State space search. In artificial intelligence, parallel systems are used for tasks like optimization and decision making. Simulations. Parallel systems power complex simulations in areas like weather forecasting and molecular biology. For instance, NASA uses parallel systems for space simulations, and companies like Tesla utilize them for autonomous driving simulations. Challenges and economic viability. While parallel processing systems or parallel systems provide significant computational power, they come with challenges. High hardware cost, that is, specialized hardware is expensive. Number 2, limited applicability, that is, not every problem can be parallelized effectively. Distributed systems, on the other hand, offer cost-effective alternatives. By using off-the-shelf networked PCs, companies can build powerful systems without the heavy cost of specialized hardware. For example, Amazon Web Service allows companies to rent cloud resources, scaling their computing power without purchasing expensive servers. As a conclusion, parallel systems offer immense computational speed and are tightly coupled, ideal for tasks requiring massive processing power. Distributed systems excel in scalability, flexibility, and fault tolerance, making them perfect for cloud computing and internet-based applications. While both systems are powerful, distributed systems are often proven to be more economical and scalable, driving much of today's cloud infrastructure and large-scale computing solution. Thank you.